Hi everybody, this is John Gardner, Professor of Mechanical and Biomedical Engineering at Boise State, and welcome to this fourth and final installment in Module 6 using Simulink to generate computer simulations of dynamic systems. So in the first three modules we talked about what, the why, and the how of simulations. We went through the basics of Simulink, and in the final Module 3 we looked at some of the tricks of the trade, a few of the little behind the scene tricks that I think will make it easier as you go through this course. So we left with this simulation here where we have a forcing function here. The summation function, you'll remember here, is the summation of forces. We have the damping force, which is velocity times b. We have the spring force, which is the spring stiffness k times x. And the mass shows up dividing into the summation of force, leaving acceleration. Integrate that to get velocity, integrate that to get displacement. So it's this nice compact graphical representation of our differential equation. And you remember when we ran this, it automatically invoked the initiation function, the script that defined mass b and k, and I can bring this up and show you that for this set of parameters. We get an oscillating system, a damped oscillating system that has an overshoot of about 60%. It's got a settling time around a second or so, and I wanted to point that out because this is one of the features of linear systems is that the characteristic of the response, the shape of the response, doesn't change with different size inputs. So this was an input of 100 newtons. If I put the input was an amplitude of 1 newton and run it again, it doesn't show up well on the scope until I rescale it, and indeed the shape is almost identical. The scale is different because it was a much smaller force, but it looks the same. Okay, so that's the feature of linear systems. And the reason I want to point that out is because we're about to implement nonlinear systems, and I want to demonstrate the effect that has. So the nonlinearity we're going to look into is a nonlinear spring. And if you think about how most springs, certainly the ones in compression, work, and in extension both ways, as they get closer to the solid height as you press them together, the coils start getting closer to each other, and it becomes harder to compress them, so it gets stiffer. Same way when you're pulling it apart, when the coils start getting too far apart, you're actually starting to pull the wire of the spring, and it gets stiffer. And one way to represent that variation in stiffness is by implementing the spring stiffness not as a linear function but as a cubic function. And if you think of the shape of a cubic, you'll remember that it's the slope of it is the smallest when it's crossing 0, and then it gets very steep as it gets away from 0. As the x-axis move along the x-axis away from 0, you get a steeper and steeper response. So a cubic spring actually could be a very good model of reality. So we're going to model that two different ways in MATLAB. So I'm going to start by eliminating that linear gain where we multiplied times k, and I'm going to bring up my block library. And so if you bring up your block library, it has all these subfolders in it, and I really like the user-defined function for this. We're going to look at two different ones. I'll start with the simplest one, FCN. You remember that if it's pointing the wrong way, you can just hit the keyboard Control-I. I thought I could. What am I doing wrong? Yep, there I go. I just had to highlight it correctly. Hit Control-I, it turns it around. If you bring it up into the diagram, plug it back in. So what this block does is it lets you implement a single line of code where the input to this block are the arguments. So it's like it's a mini function. And if you had a multiplexer on the front end, you could have several different inputs. We only have a single input here, but the input, the default in MATLAB is the input of these blocks is u, the vector u, and if it's a single input, then it's u of 1. Okay, so this piece of code I'll say is k times u of 1 raised to the third power. So instead of the force of the spring being kx, the force of the spring is kx cubed. And I'll hit OK. Simple as that. Run it again. So now remember, my constant, now I have a force of 1. I can already see that it changed the nature of the response a little bit, changed it quite a bit. So it's swinging bigger through here, and much less overshoot, a much slower response than it was with the simple K. Um, but remember this one. So let's characterize this with an input of 1 Newton. We had an overshoot of, oh, not very much. It looks like the steady state's going to be about 0.22, and its overshoot's about 0.24. So it's only a modest amount of overshoot, maybe 5%. And it was settling down in about a second. Okay, so let's make the input bigger. Let's make it 10. Run it again. Now I'm going to have to rescale it because it's a bigger force. It'll have a bigger response. But not only did it have a bigger response, the characteristic of the response has changed. We're moving up now into a different part of that cubic curve where the slope is steeper, meaning the effective spring stiffness during this response is bigger. And so you're seeing more overshoot and a longer and more oscillation, so higher frequency as well. Let's keep this exercise going. Now the input's 100, and again it'll be bigger, but also much more oscillatory, much higher frequency. Notice the time scale hasn't changed. These are 1 second simulations each time. So we're getting more overshoot. We're up to about 40% overshoot, and so on. So this is one of the things you find with nonlinear systems is that you can't generalize about the response. If you work in different places in its operating space, you're going to get different kinds of responses. So that's a very interesting thing to explore, and you need simulations to do that by and large. Okay, so that's one way to do it. Just implement this the FCN, the f of u function. So let's look at another way that lets you do even more complicated functions. Is the MATLAB system. I'm sorry, no, not that one. MATLAB function call. Okay, so I do a control I on this to turn it around. And if I double click on here, it actually brings up the editor window with the skeleton of a function called FCN. Now I could call it something different. Let's do that. Let's call this, instead of FCN, I'll call it F cube spring of u. And I'll say F equals K times u raised to the 3rd power. Now I could run this and it'll get an error. Okay, so let me save it. It's now called spring function. Now you see it automatically, MATLAB automatically changed the name of the function to f cube spring. And I'm going to run it, and I predict it's going to give me an error, and I'm going to let you think about why that might not work. What did I do in here that might violate the operating rules for MATLAB? Okay, think about that. You might want to put it on pause for a second because I'm going to run it now. And sure enough, I got an error message. Here's the error message. It says undefined function or variable k inside MATLAB, inside a MATLAB function. And it says line 3, column 5. So I'm going to get rid of that window. Line 3, column 5. Sure enough, here's k. And it's because a function, we talk about in computer programming, we talk about scope, right? The scope of a function is just what's defined within that function. It doesn't have access to any of the variables defined outside. And this is just one of the kind of difficult things you need to deal with in MATLAB. There's a couple ways around this. I'm going to take the easiest route and say, okay, just going to hard code it. So I'm trying to remember what value I used to have for k. So k was 100. Okay, so I'll keep that value of k, and I'll just say I'll just hard code it in here. Pretty bad programming practice, but for the time being, we'll leave it at that. So I can save it. I'll bring my window back up. Excuse me, I am just having a hard time finding the window. There it is. Okay, so there's my f cube spring. Now when I run it, it runs just fine. Took a little longer to figure it out, but there's my force. And so there was how I left it, right? That was with an input of 100, and it implemented exactly the same function, just did it a different way. So if I go back to my input of 1 Newton, we'll get the very lazy, slow response that we saw the first time. like that. It's another way of looking at it. So nonlinearities are just a big part of what we do with MATLAB, and a lot of what goes on in Simulink helps you look at those nonlinearities. The easiest way, or the most general way of implementing them, is with these functional calls. Let you go ahead and open up a script and just define it with math. Sometimes you might want to, you could actually use the individual math operators in Simulink. Let me tell you what I'm talking about here. So if you go to commonly used blocks, talk about math operations, there are all sorts of blocks that let you do multiply and divide and add and absolute value and things like that. All very useful, but after a while, and we could have done this for like the spring, for example, but after a while it gets kind of goofy. If the number of blocks and operators in this window that we see here is so complicated that you can't really see what it's doing, then why bother, right? The power of Simulink, of these block diagram oriented approaches, is the visual simplicity of it. You can look at this, and if you know what you're looking for, you can spot this right away. If you spot it right away, this is a second order system, and it's analogous to a spring mass damper system. Could be an RLC electrical circuit as well, but they all have this same structure. If you start messing it up with a bunch of multiplication and extra summing junctions and things like that, it's going to be harder to see. So it's easier and it's better practice to embed this in a function call like this. So that's the last thing I wanted to talk about. This is adding nonlinearities and making this the most general thing possible. And we'll wrap it up now. Thanks very much.